Hello everyone, thank you for listening to my talk on our work, Hidden Screen Camera Communication on Invisible and Inaudible Dual Channel. This is Qian from the University of California, San Diego. The work is done when I was a PG student supervised by Professor Zheng and Professor Yunhao in Tsinghua University. Billions of videos are created and viewed every day and everywhere. For example, advertisements, streaming videos, and movies. An audience would like extra information about the video contents they are interested in. For example, a second advertisement video describing the usage and function of the product, or a low-quality version of the movie for video sharing, or some augmented reality content for an AR video. Existing works explore the hidden screen camera channel to embed extra information in the primary video unobtrusively. That is, they mix video frames with high-rate complementary data codes. On one hand, human eyes cannot perceive the change, since they are insensitive to high-rate flickers, which is known as the flicker fusion property. On the other hand, a camera with a high capturing rate can detect the flickers and decode the data. A practical hidden screen camera communication method has to meet three complicating goals: high invisibility, high throughput, and high reliability. Our previous work, ChromaCode, achieves a throughput of 551 kilobits per second and a bit error rate of 8%. However, it still hardly meets the requirement of the multimedia applications mentioned above. We reveal two causes of limitations of existing works. The first problem is the failure of screen detection. There are two main types of screen detection algorithms, the rule-based one and the learning-based one. The rule-based one uses some rules to detect the corners, edges, and finally the quadrilateral of the screen. ChromaCode uses the rule-based algorithm. The learning-based one uses some machine learning models to detect objects, including the screen. However, both of these methods fail to detect the screen opportunistically, mainly due to the complex surroundings of the screen in practice. We further evaluate the impact of the detection error, as shown in the figure below. Bit error rate explodes with a detection error of only several pixels. The second problem is the failure of metadata decoding. Existing works, including ChromaCode, embeds metadata together with data in video frames. However, the screen camera channel is known to be very noisy. As a result, the metadata may not be correctly decoded, and the whole data frame is thus ruined. We ran experiments with ChromaCode and found that 24.6% of frames have bit error rates over 8%, where 29.3% are due to metadata decoding failure. To overcome these problems, we propose AIRCODE. On one hand, to achieve accurate screen detection, we explore visual odometry to track the screen. On the other hand, to achieve high reliability, we split data and metadata and embed metadata in more robust audio signals. First, the screen detection process of AIRCODE follows the standard process of visual odometry, yet with extra function for screen tracking. First of all, upon receiving a new frame, AIRCODE extracts visual feature from it. If the visual odometry has not been initialized, AIRCODE uses the rule-based algorithm to detect the screen and decode the data. It then selects two successfully decoded frames to initialize the visual odometry, that is, to estimate the camera pulse between the two frames and initialize a global map which consists of 3D locations of common feature points of the two frames and 4 screen corner points describing the 3D location of the screen. Next, AIRCODE continuously tracks the camera pulse of the newly arrived frames and projects the screen on the frames and decode the data. When the decoding of the new frame fails, AIRCODE generates a second candidate with a rule-based algorithm and merges it with the tracked screen. The figure below shows an example of the tracked screen and the merged one. Finally, AIRCODE periodically selects new keyframes to update the screen to avoid drifting error. When a new keyframe is selected, AIRCODE first jointly optimizes the camera poses of the keyframes and the 3D locations of the feature points in the global map. It then optimizes the 4 screen corner points by minimizing the reprojection error of the screen corner points on the keyframes. The right figure shows an example of the global information maintained by AIRCODE, including the screen, keyframes, and map points. Second, AIRCODE splits data and metadata and explores screen camera channel to convey data, while uses the speaker microphone channel to convey metadata. To robustly transmit metadata via audio signals, we have to overcome several challenges of the audio channel, including long reverberation period, which causes inter-symbol interferences, strong spectral leakage, which may be audible to human ears, and the frequency selectivity of audio devices, which leads to decoding errors if not properly equalized. For reverberation, we adopt a long packet duration, as shown in the left figure. A packet is 67 milliseconds long. Besides, we separate preambles and data symbols in the frequency band. As shown in the right figure, the preamble is assigned to 20 to 22 kHz, while the data symbol is assigned to 17 to 19 kHz. For spectral leakage, we apply a typical same window to every preamble and data symbol in each packet. For frequency selectivity, we adopt Manchester coding to encode 1 bit with 2 adjacent subcarriers. Since the adjacent subcarriers experience similar channels, the receiver can simply decode 1 bit by comparing the amplitudes of 2 adjacent subcarriers. The video frame of AIRCODE is based on that of chroma code. Thanks to the use of the audio channel, AIRCODE saves more coding space in video frames for extra data, while achieves more reliable communication. We evaluate AIRCODE in terms of raw throughput, data goodput, and BTR rate. We also conduct user study to evaluate the insensibility of AIRCODE. 5 representative videos with various scenes and songs are selected. We compare AIRCODE with 2 state-of-the-art works, Chroma Code and InFrame++. As shown in the figures, AIRCODE achieves a consistent throughput of over 1 megabits per second and an average BTR rate of 5%, which outperforms Chroma Code and InFrame++. For the audio part, AIRCODE maintains the BTR rate consistently below 1%. We further evaluate the performance of screen tracking. As shown in the figures, AIRCODE detects the screen correctly in over 97% of frames across different types of videos, and all tracking errors are within 9 pixels. In contrast, Chroma Code uses a rule-based algorithm and has large detection errors, especially in videos with complex textures. We then conduct ablation study. First, the VO-based screen detection achieves a lower BTR rate and a much higher goodput than the rule-based one, thanks to more accurate screen tracking. And second, by embedding metadata in audio signals, a higher throughput and goodput are achieved, since more coding space in video frames is saved for embedding extra data, and the metadata is more reliably transmitted via the audio channel. In conclusion, in this paper, we present AIRCODE, the first system that achieves considerably high data rates of over 1 megabits per second, thanks to the design of the VO-based screen detection and the use of the invisible video and inaudible audio dual channel. We prototype AIRCODE and evaluate it with experiments, Please refer to our paper for more results. Thank you for listening, and I'd like to take any questions.